Okay, so in the last lesson, we discussed Fibonacci and how you don't want to solve Fibonacci recursively. It'd be much better to use dynamic programming or some other way of doing it. Then we looked at kind of I consider this like the hello world of dynamic programming, that you solve the coin problem. And the problem was this, that if you're given a set of coin denominations, can you find the optimal number of coins that you need to give change? Ideally, we want to minimize it. And the process was that we created an array that was that had its last index equal to the amount of change you want to return. And so I think that's one of the most confusing parts about dynamic programming, is that we're not used to the index of the array representing something. In this case, the index represents the amount of change we're returning. And we were able to build up from there. We started with, we said that we built this array out, and we actually filled this all with infinity, which wasn't truly infinity. It was just a large integer that we called I for infinity. And we asked ourselves, could we make a base case to build from? And we said, yeah, sure. Index 0, which actually, this is the index here, which actually represents the amount of change in cents I'm trying to return. I know how many coins I need to return. I need to make 0 cents in change. Obviously, it's just 0. And then we built up from there. And you'll recall that we had different denominations. We had 1 cent, we had a 3 cent, a 7 cent, and an 8 cent. And just because of how that worked out, these kind of unusual denominations, we were able to solve for the amount of coins it would take. And you can see it took more coins to make 2 cents than it does 3 cents. We're not unfamiliar with that. It takes you 4 coins to return 4 cents, but if it's 5 cents, I only need 1, just in regular U.S. currency. So that's not that unusual a thing. And we went out and we just kind of drew out a solution for 15 cents, and we said it only takes 2 coins. So we were able to say how many coins we needed, but we were not quite able to say what those coins were. And that's what I want to tackle now through a process called backtracking. Okay? So once you figured out this dynamic array, I believe we called it DP, this index here represents the solution. This is the optimal amount of change. And what I want to do is I want to start there. So I'm going to put an index there, and I'm going to look at each one of these coins, and I'm going to see if I used them. So let's start with coin cent 1. Well, if I used a 1 cent coin, that means that I must have at some point had 14 cents. But when I look at the solution for 14, I see that there's 2 coins there. So that means that I did not create 14 cents and then add 1 more penny to get 15, because otherwise that would have been a 3. So because this 2 is not it's not less than, let me zoom in a little bit. This 2 is not 1 less than this number of coins here. I disregard that. The next denomination we looked at was 3. So let's take a look at the 3 now. So we're going to say, okay, well, maybe the last coin that I put in was the 3 cent coin, in which case 15 minus 3 is 12. Well, that's actually even worse, because there's like 3 coins to make 12 cents. So that's not the right answer either. All right, let's try again. Let's try the, I think, 7 cent coin. 15 minus 7 is 8. Well, look at that. That only took us 1 coin to make 8 cents. So that's what I'm going to say was the coin I gave. So I gave a 7 cent coin. Now, to make 8 cents, it apparently only takes 1 coin. Again, I check each one of these. Minus 1, nope, that's not 1 less. Minus 3, that's not 1 less. Minus 7, that's not 1 less. Minus 8. So we must have used an 8 cent coin. Once I get down to change 0, I know I'm done. So we use a 7 cent coin and an 8 cent coin. And it turns out that sometimes there's multiple correct solutions. In this case, we could have gone an 8 cent coin and then a 7 cent coin. It doesn't matter. That's the same answer. Sometimes you get 2 different answers, but you will get at least an answer for what change to give. So you can tell someone, and you could use this to say, hey, give exactly this amount of coins, give them these coins. All right, let's take a look at how we can code this up. So, a couple different things we could do. We could use a matrix where the matrix is associated with like a coin type. We could also use a map. I'll tell you what, it's probably been a good minute since we've used a map. Let's use that. Let's see, do we want to use a hash map or a tree map? I think it's actually going to turn out to be kind of the same because we're using integers, but I'll go ahead and do a tree map. Okay, so we've already found our solution here for the number of change. I'm just going to, instead of returning that value, I'm just going to go ahead and print. So I'm going to change this method to void, and we'll just kind of print out what coins we need. Okay. So map, we're going to do a map from integer to integer. Okay. All right, so we're going to be starting our index at exactly the amount of change that we're returning, because that's the last index. So I'll say int index equals change. While the index is greater than 0, so when we get back to 0, we're done. I got to loop through each coin. So I'll just use that for each loop we used earlier. For each value of coin in my values array. Remember our array of values were the denominations 1, 3, 7, and 8. If so this is me asking if the value at my current index, which means the number of coins it took from my current value, is one more than the value of my, I'm sorry, we're using index, not current. My current index minus, V for value. I'm looking at two different code here. So if what this line of code here is me saying, like we were here, if the value here at my current index, which is 2, if I subtract 1 from that and it gives me the value at my current index minus my coin value, if that's the case, then I found an eligible coin that we could have used. Okay? And this is how I'll handle it. I'll add it to my map if it's not there. If map.get my value equals null, then I need to put it there. And we're saying we're mapping the value of the denomination to how many coins we need of it. Right now it's just 1. If it already is there, that means that coin has already been there. That coin already exists in our map. So we just need to add to it. So I can say map.put value map.get value plus 1 more coin. And I'll move my index by my value. And I'm going to add a break. And that's pretty important because I don't want to keep doing this with the other values in the array. So I'm breaking from the for loop. There we go. And when I'm all done, I'm just going to print it out. So remember, map.keyset returns the key set, the set of keys for your map. I'll say map.get coin value. So I'm just going to get how many coins we use for that coin value and say coins of denomination coin value, so that I know that it's telling me how many of a specific type of coin to use. All right, I think that's everything. Yeah. Okay, let's try it. Well, I say there's no time like the present. Let's start with what we started with. Let's do 15. So let's solve it for 15 cents. Says we need 1 coin of denomination 7 and 1 coin of denomination 8. That is an optimal solution for how to get 15 cents using our strange denominations. Let's try it again. How about 78 cents? Huh. Currently, we need 8 coins of denomination 8. That would be 64 cents plus 14, which would be, what did I say, 78? Let's do 77. Huh. 56 plus 21. 77. Okay. Let's try 76. Wow, this is really interesting how that 7-8 denomination gets us a lot of coins. That's 48 plus 28. Okay, 73. Let's see if we can find something I can't do. Oh, 9 coins of denomination 8 and a single penny. 71. Let's try that. Huh. It's really interesting that 7-8 combo just keeps giving me stuff. Probably some sort of math riddle about that. Hey, 1 coin of denomination 3, 8 of denomination 8. All right, well, I hope you enjoyed that. So it's time to do a problem.